1, 3, 7, 15, 31. You already have it. 2 to the n minus 1. It took you a second. The textbook does not do that. It rewrites the recurrence, spots a geometric sequence hiding inside, and lands on the same answer 5 lines later. So which one is better? And if the fast one is fine, why does anybody write the slow one down? Here is the answer, and it is not what people usually say. The tidy method is not better because it is rigorous or because it is shorter. It is better because it keeps track of what the quick method throws away. The quick method hands you a candidate. The tidy one hands you the boundary, which things are actually attained and which only look like they are. So carry both. Use the quick one to find out what is probably true, and the tidy one to find out where it stops being true. Let us make the distinction sharp, because it is not about elegance. A method is well-mannered if it survives a change of the numbers. It is badly behaved if it stops working or turns monstrous the moment somebody edits the problem. Guessing from the first 5 terms is badly behaved. It is not wrong. It is just fragile, and fragility is a property you can measure. Change one coefficient and watch it die. So why keep a fragile method around at all? Because the well-mannered one is a trick that fits a shape, and one day the problem will not have that shape. When the standard move fails, the only thing left is the pile of half-legal maneuvers you have practiced. And there is a second reason, quieter. Trying the bad method is how you find out what the good one was doing. Until you have seen it fail, you have not seen what it protects. Watch the fragile method work, then break. Back to 1, 3, 7, 15. Guess 2 to the n minus 1, then check the difference. Each term is one more than double the last, and the gaps run 2, 4, 8, 16. A geometric sequence, and the answer follows. Or kill the plus 1 instead. Write the recurrence twice, once at n and once at n plus 1, and subtract. The constant cancels, and what is left says the gaps double. Same conclusion, no clever rewrite. Neither is the textbook method. Both are correct. The subtraction root deserves a closer look because it generalizes further than the guess does. Write the rule at n, and again at n plus 1. 2 equations, both carrying the same nuisance constant. Subtract them and the constant is gone, because it was the same constant both times. What remains says the gaps between terms double. The first gap is 2, so the gaps are 2, 4, 8, 16. Add them up from the start, and you have the answer without ever noticing that anything was geometric. The trick was not cleverness. It was refusing to carry a term you did not need. Change the plus 1 to plus n. Same shape, one symbol different. The reflex is to shift by n, the way we shifted by 1. It does not work and the failure is total. The shifted sequence is not geometric at any step, not for a single n. But look at how it fails, and it tells you the fix. You need to shift by n plus 1, not by n. Then the sequence doubles cleanly, and the answer is 3 times 2 to the n minus 1, minus n minus 1. The failed attempt was not wasted. It pointed. One more edit to see the fragility plainly. Start at 2 and let each term be 8 times the last plus 4. 2, 20, 164, 1,316. Guess that. Nobody can. The closed form is 18 times 8 to the n minus 1, minus 4, all over 7, and there is no way you were reading that off the list. This is what badly behaved means precisely. The method did not become harder. It became unavailable. Now the example that pays for the whole lecture. Two lines. The first is y equals tx. The second is x plus ty equals 1 minus t. Let t run over everything from minus 1 upward and follow where they cross. The badly behaved move is irresistible. Solve for t from the first equation, substitute into the second, clear the denominators, and see what falls out. What falls out is a circle. Center 1/2 minus 1/2. Radius 1 over root 2. 30 seconds, and you have a beautiful answer. Except the crossing point never visits all of it. The reached part is an arc of exactly 270 degrees. The missing piece is exactly 90. 1/4 of the circle, 180 points out of 720, never reached by any allowed t. That quarter is not the locus. It is an artifact of dividing by something that was allowed to vanish. The tidy method does not have this problem, and now you can say exactly why. It never asks what equation the point satisfies. It asks whether a legal t exists that puts the point there. That question carries the boundary with it, and elimination does not. So which part of the circle is real? The endpoints are worth naming, because they are where the two methods disagree. At t equals minus 1, the lines cross at the point 1, minus 1, and that point is on the circle and genuinely reached. As t runs away to infinity, the crossing point slides toward the origin, and the origin is on the circle too, approached but coming from one particular side. Between those an arc. Outside them, a stretch of circle that satisfies the equation and is never visited by anything. Elimination cannot see the difference, because to elimination a point either satisfies the equation or does not. So the division is not tidy versus sloppy. It is candidates versus boundaries. Elimination, guessing from a few terms, ignoring where a denominator dies. These are all machines for producing something probably true fast. That is a real service, and you should use them without guilt. But none of them can tell you where the truth stops, because every one of them works by forgetting a condition. That is what makes them fast, and the honest limit on the advice itself. A wide repertoire is not a substitute for knowing which tool you are holding. Reaching for the fragile method on a problem that has a standard shape is not resourcefulness. It is just a longer road. Keep your pockets deep. Practice the disreputable methods on problems that do not need them, so they are there on the day something does. And when the fast method hands you an answer, ask the one question it cannot answer for you. Which part of this is actually reached? The quick way finds the shape. The careful way finds the edge.